Hello everyone, welcome to the class ECE317. ECE317, the 14th week is a Wednesday's class. Alright. Today we will discuss the Fourier transform. Fourier transform, the numerical method to calculate the Fourier transform of a signal. Okay, this is the last part of this course, and it won't be included in the exam, and no homework actually, just a kind of interest. Alright, yeah, consider the numerical. Fourier transform. Actually, this is the we call it a fast Fourier transform, FFT algorithm. We have I forgot which one, but we already have one class introduced the how to calculate the Fourier transform, right? Suppose we have continuous time signal xc of t. I suppose some signal xc of t. Then how to calculate this? Yeah, by definition you have continuous times Fourier transform, and you have this one by definition equal to something, and you can take samples, then those samples give a discrete time signal, and that discrete time signal you can have a x of e to the j omega if x of n equal to xc n t. We have this one. We also have formula in a part with sampling theory, right? And then both these two you cannot calculate directly because this is a continuous time, the whole curve, right? You have infinite values, and this one you also need, by definition, this will be a summation of x of n for all the n's and run from negative to positive infinity, right? Into this one, you cannot really calculate the infinite summations, right? You can only have finite. So what we can do is xn equal to xcnt, which only for and run from like 0 to n minus 1, totally n numbers. We have this one, and then we can have capital X of k equal to, this is summation of x of n e to the negative j omega. Now omega is not all omega. We pick some omega. There will be 2 pi over n times k related with this k. So this is 2 pi over n times k. This is the frequency of this capital X, right? Like this is x, capital X with some frequency omega, right? This is capital X with some coefficient, some frequency k. K is actually the frequency in this one. Okay, then k, the n run from 0 to n minus 1, and for each k you have capital X of k. So k run from 0 to n minus 1. So we have this. We call this as DFT, discrete Fourier transform. Actually, we already calculate this one. This one and this one, what is the relation? This one will be suppose like looks like this, and this one according to some symbols like here, right? Some symbols, but not exactly on the curve. This kind of approximate, right? So this is the way to calculate by computer. You can really calculate just these numbers. They are not exactly equal to this one, but it's kind of approximate. Okay. Now we consider how to calculate this. You just follow the formula. This is the most basic way, but this way will cost a lot of time. Then the basic idea, we have two considerations. We call this is a DFT of endpoint. Endpoint DFT. We take ensembles. Right? Ensembles. We take ensembles, and after you perform the DFT, the result is also ensembles. Right? K run from 0 to n minus 1. Here's n run from 0 to n minus 1. So both the sample value of the signal, it is endpoint, and the resulted Fourier transform values is also endpoint. There are some sample point from the Fourier transform. Actually, it is this part and this part. This is a capital X0 is here, and this one is a capital X of n minus 1. Remember last time in the lab you should know this is kind of this part. It's shifted to here, right? Okay. Now we try to find a way how to calculate this. Then we have two basic considerations for fast algorithm. We need two factors. The first one, 2 point DFT. What is this? Only 2 point. Okay, then sample of signal. Samples of signal really have two, x of 0 and x of 1. And then you perform DFT. You will have capital X of k. I just copied the formula, right? Now is the summation n run from 0 to capital N minus 1. Now capital N is 2. Capital N is 2. So here's 2 minus 1, it is 1. And x of n times e to the negative j 2 pi over n is 2. Capital N is 2 times k. Right? This is exactly that one. Now I write term by term. First term n is 0. So this is x of 0 times e to the negative j. Okay, you see 2 pi over 2, it is just pi. So I just put pi n, sorry. I lost n here. I'm sorry. Yeah, kn. Yeah. Now here is a k is 0 times n. Not k is 0. K is k. N is 0. Right? The first term n is 0. And then second term n is 1. So x1 e to the negative j. So I lost the pi. Right? This is just pi. This is just a pi. And times k times n is 1. Yeah, these two terms. Okay, I write again. X of k equal to x of 0 times what? The power is 0. Right? So this is just 1. So this is just x of 0. And here plus x1 times e to the negative j k pi. And k run from 0 to n minus 1 is 1. So we have these. Alright, right, let me give more details. Capital X is capital X. Capital X of 0 will equal to x of 0 plus, now k is 0, so this power is 0. E to the 0, it is 1. Then, okay, this is just x1 times 1. And the capital X of 1 equal to x of 0 plus x of 1 times this exponential power. Now is e to the negative j, k is 1, so it is pi. What it is? This is cosine of negative pi plus j sine of negative pi, which is what? Cosine negative pi. Cosine negative pi. So this is negative 1, right? The cosine pi, same thing, negative 1. And j times sine pi, sine negative pi is 0. So it is just negative 1. Alright? This is just negative 1. So here is just minus. Okay, we get this. You see? For 2-point DFT, the calculation you only need one summation, one subtraction. It's quite simple. Quite simple. So we can apply this factor to reduce the whole calculation. This is the first factor. Okay, we need 2 factors. Now look at the second factor. Second factor, if n equal to 2m, now n is the totally number of the samples, right? It's an n point. We consider n point DFT. Now suppose n is an even number. It is 2 times some m. 2 times m. Now capital X of k. Here k is run from 0 to n minus 1. It is also k run from 0 to 2m minus 1, right? Same thing. N is 2m. Equal to, now is a summation. Just copy that. Yeah, it is just this one, right? Let me write term by term. It is x of 0 and equal to 0. Then times e to the, here you have n, so this first term is e to the 0, right? It is 1. And x of 0 times I use that w equal to e to the negative j 2 pi over n. Okay, like this way. Then here is a, this is a w to kn, right? This is a w to the k times n. K times n. Now k is k, but n is a 1, so this is a k. And x of 1, w of, now is 2k, n is 2, the 2k. Yeah. Plus x of, the last one is n minus 1. Here's w, there will be n minus 1 times k. We have these. Okay, now what we can do? We separate the whole summation as 2 parts. Separate the whole summation as 2 parts. The first part is even terms, and second part is odd terms. So it is a f of 0 plus x of, sorry, this is 1, this is 2. Yeah, 0, 1, 2 until n minus 1, this is x. And the power is 0, then k, 2k until n minus 1k. Okay. Then this one, okay, I put this again. The first term, then I use all the even terms. This is x2, w2k, plus until this is n minus 1 is 2n minus 1, right? 2m minus 1. This is this. And the one term before these, there will be x of, this is also 2m minus 1. So one term before, there will be 2m minus 2. This is even number. This is even number. And w here will be 2m minus 2 times k. Okay, all the even terms. And then the other terms, x of 1 plus x of 3. Here will be w 3k. Right. is the last one, this one, x of 2m minus 1, w 2m minus 1. Okay, I write in this way. Then you can see what it is. This is also a kind of Fourier transform, right? Fourier transform is the signal value times the power of the exponential power to summation. Now it is also signal times exponential power do a summation. So this part, it is already a Fourier transform, but the orders change. Every now is every w square you think is similar with that w, right? W square similar with that w. Actually, this is a endpoint DFT. This one is an endpoint DFT, and this part. Oh, I lost the W1K here. This part, I can move a WK outside. Then it will be x1 plus x3 w. I move 1k out, so here's a 2k plus until last term x of 2m minus 1 times w 2m minus 2k. Right. I remove 1k out. Here I need a minus 1 more, so minus 2. Right, this way. Okay, this part. This is also an endpoint DFT. So you can see, we want to calculate this one. We can calculate 2 shorter, the half of the point, the DFT, right? DFT, they are also DFT. The DFT of all the even point values and the DFT of all the odd point values. Each one, the DFT, the length of DFT is a half. So you can imagine, for example, you start from n is 1024. That's 2 to the 10th, right? 2 to the 10th. Then you can write it as a 2 part, each only half of the length. Each is a half point, still DFT, but half point. And each part you can continuously do half and half until the length of the point go to 2 point. In 2 point, you just do plus and minus. So by this way, you can save a lot of time. You got it? Okay. All right. So let us do some work in the MATLAB. We have this in the textbook. This one. Then. Okay, the first is x0, 2, 4, 6. They are even point. They do half of n DFT. And here x1 to x7, the odd values, also do half of point DFT. And then the result combined together, you get the final result. Okay, so by this way, like 8-point DFT can be realized as 2 half point, the 4-point, half of 8, so 4-point DFT. And each 4-point DFT can be realized as 2 part. Each 4-point can be separated as 2 2-point. Then 2-point, for 2-point DFT, you only have summation and subtract. Summation and subtract. So this can save a lot of time. Right? Okay. Now let's work in MATLAB. Okay. MATLAB. Well, if you just work do all the work in MATLAB, then this part is not necessary. However, if you have a chance, like later you need to work in a different way for the different situation for the programming, you have to use C or Java or something else, but you need for the transform, then you need to write your own for the transform program, right? So how to do it is okay, let me edit. Now this one is a little bit large. I edit several things. First thing I edit I just say DFT 1. This is original one. Okay, this is original one. This is original one. This is a function my DFT 1. It will return a capital X, and the input is a lowercase x, or I put the n, and it is capital X K. Alright. So I want to find the DFT of capital lowercase x n. So xn will be a vector. I don't know the size, so size of it, like a and b equal to the size of xn, and not a and b. This is a vector, so one of a should be 1. If a is 1, then b will be the size. B will be the size. So I say n is b. Else, if b is 1, then n is a. Right? Let me show both. Okay. These put it here. This one. The formula is just like this. The formula is just like this. So we want these coefficients. These coefficients times the input value. So the yj. So y equal to 1 to n. So j run from 1 to n. In MATLAB, all the indexes start from 1, not from 0. So here we run from 0 to n minus 1. But inside the program I need to use 1 to n, not 0. I will be the imaginary, the square root of 1. So I use k. K equal to n and k. Okay, n and k, just n and k. For every just k and n. K and n. It's a lowercase n. Already be confused? I use capital N plus 1 here. Alright. Okay. Next one. Then I need to calculate the capital XK. Capital XK. XK of k equal to 0. I started from 0. Maybe I need to give the size of x firstly. XK equal to zeros of 1 and 1. So I start from a vector with all the values are 0. All values are zeros. And now I gave, then I don't need these, right? I do not need these. XK of k equal to xk of k plus one more terms. There will be xn of n times the exponential power, that is negative j omega times omega 0 times omega 0 times omega 0 times k times n. So capital X, after this n, I have capital XK. Then I have next capital XK. Just return capital XK. Okay, that's it. Save it. And I need to add it another. Then I added a new file. It's a lecture 14 Wednesday's class.m. and run it. It is a program like this. And okay, this one I will use that my DFT. So I give x equal to randomly like a 1 32. Okay, 32 point. This is a random value with 32 point, and capital. Okay, this is just x. Then I have y. Y1 is my DFT1 with x as input, and y2 is FFT of x. Right, I have y1 and y2. I want to see whether they are same. So I check the maximal value of absolute value of y1 minus y2. Subtract them, right? I minus them, take the absolute value, check the maximum. If these return a small value, then they will be good. See? Okay, let me run it. This is a lecture 14 Wednesday. Undefined W0. Oh, I lost W0 here. W0. Yeah, before I start, I need W0, which is 2. There will be 2 times pi over n. Right? This is W0. W0. So e to the j times 2 pi over n, the k and n. Okay, this one. Run it again. Oh, it's somehow large. I guess something wrong. Let me see. It should be a small value. And y is 32. Okay, and it will be good. And then xk start from 0, and xk is xk plus xn times exponential power negative j omega 0 k2. Oh, here. This is here I need to use -1. So inside this power, this will be k minus 1 and n minus 1, right? Going from 0 to n minus 1. Okay, this will be good. Save. Okay, now it's good. You see, the difference is some value times 10 to the negative 14th power. So it's a very tiny value. Okay, we have same value. And so that means our result, my DFT1, the function, the result is the same as the FFT. Okay, these two are same. but the time will be totally different. We can try, for example, just try, I don't know the time, I will see, okay, the time here, like a clock, A equal to clock, this gives the time, and run my DFT, the B is also clock, then I need a time T, which is a B minus A. This will be a vector. B minus A, there will be a vector. The clock, they contain several values. Clock. Okay, the year, right? Year, month, day, and then hour, the minutes, and the second. So the first three should be same. Then last three, I combine them together as second. So when I use to calculate this T, I gave I say it's P. P is 0, 0. First three are zeros. 0, 0, 0. And then hour to second, there will be this one, and then minutes to second, the one. Okay, this is P, and the T equal to this one times P. The P should be column. Okay. All right, and then I do the same thing for the FFT. A equal to the clock. This is the time before we started, and B is also equal to clock. And T is the same. Another T. Okay, I have another T. Both T. Then we can see the calculation clock, not clock, Lec14W. You see, 32 point. Use my DFT, I spend times 0.008 second. It's a tiny bit, you can measure it's 8, but the second way you calculate the time is still 0. It's just some time, but very short, right? So they are very faster. If you want to try a little bit larger, is 32. If I change this, like I use 124, what will happen? Oh, that's too much. If I give like 64, 128, 128. All right. FFT also needs some time, right? 0, 0, 1. T is also some time. T is our DFT. Our DFT is like 100 times more than the FFT, right? Spend more times, 100 times of the time cost. All right. Now we try to reduce it. Okay, I added a new one. Added my DFT2 dial. Okay. What it is? Okay, DFT2. Things will be similar with these. Actually, this I can copy this and make some changes. Copy. Alright, first part is same. I try to find the size, and here I want the size is the power of 2. Okay, so just remember it. Then I have N1. Oh, I don't need N1 anymore. This one. N1 is okay. I still have W0. I have this part, right? This is the old one, But now we will do it in a different way. We will work in a different way. I choose some odd value, some even value, and go inside it again. Okay, so here I use the xn is the input, right? So x, I use xe, which is xn. Now is 1, 2, 2 and 1. Okay, what it is? These are the even point, the even values. Even value, right? And xo odd, right? This will be xn. Now we start from second value, and we step 2 until the end of the vector. So they are the odd values. Odd values. And then I will perform xe. Let me see. I use a u e equal to. Okay, it's still my DFT 1, but another one, I say DFT 2 of xe. This is a UE, and the UO, this is my DFT 2 XO. What is DFT? Okay, I open the new one. The new one is actually same with this. After I finish, I copy it today. Okay, now xe and xo, they are half of the size. Oh, I need the if. Okay, here. If if n1 is 2, and 1 is 2, then the return xk of 0, there will be xn of 0 plus xn of 1 or 2. No, not 0. Right? You have to start from 1 index. Forget that. If you use C, that will be same. You see the index start from 0. If this one is 2, I have xn these. Capital XK of 1, there will be xn of 1 minus xn of 2. Yeah, else. Else, okay, else that means the size is larger than 2, then we need to do more calculation. We need a W0. I need to separate x to even part and odd part, and the even part perform DFT again, but the size is half, right? Then then I need a xk. So what is xk? Xk is a combine of. Okay, so k run from 1. I need the half of it, and then to m. I need m. M is 1 over 2, half of it. For k run from 1 to m. Okay, I need xk equal to UE, the even part. The even part of k plus the odd part. U odd part of k. And times power. times the power. Okay, exponential power. I put the exponential power here. This is the exponential power negative 2 times j, negative j times 2 pi over n1. I have this, right? This is xj of 2 pi over n. Alright, and here will be w0 to the power. So here I don't need exponential power. This is just w0 to the power is like this, right? w0 to the not n. I don't need n. Let's check the formula. What is the formula here? When I separate them, it will be here, right? So xk equal to the half point. This is the even part, this is the odd part, and the times wk. So here's xk, here will be wk. Right? So here's a k, here will be wk, no n, just k. This is a k run from 1 to n, and also I need xk for larger n, the k plus n, larger than n, right? This part very similar with these. Let me see. This part equal to. This is equal to uek. Ek, yeah, this will be k. Then ok, okay, and times w0 to the power k minus 1. This also need plus n, Okay. All right, I think it's fine. Then let me Control R, copy, and put this in here. Why I need a 2? Because here I use this function itself, right? You see, this is my DFT1, and here I use my DFT1. I can't use it. I need to use DFT. I use DFT2, and in DFT2, this is DFT2. I go back to DFT1. Oh no, this is a sorry, I confused. This is a DFT1, and then this is a DFT2. So this is DFT2, and in DFT2 I need to use it again, but I can't. So if you write program in C, you can, but in MATLAB it cannot work like this way. So I use another DFT3, but DFT3 it is exactly the same as DFT2. The only thing is here I go back to 2. Okay, then I'll be fine. I think. Save these. This is a DFT3. Okay, so I have DFT2, DFT3, and try to, and here I use DFT. Okay, I use one more, so I can compare 3 of it. Do I? Oh no, here I just try a second. Try whether it works. Alright. Run it. Undefined function, my DFT2 in line 5. Oh, I didn't save it. This one, save. Save. This one actually needs save. Sorry, I lost it. I forgot to some. I have. Come on. Oh, we lost this one. And here also lost this one. Okay. Say. I didn't compare. I deleted that part. The compare of it. Let me see. Which is deleted. I have y1 and y2, and I need maximum of absolute value of y1 minus y2. Right? y1 minus y2. Okay. See. Alright. You see, the value is quite small. And the time, yes, they are slow, but we can compare more. We can compare with the 3, our first and the second. Okay, this is my DFT2, and I also copy DFT1. My DFT1, this is just start from the former, and the DFT2 we consider some, as we discussed, so this should be run faster. And last one is just the FFT from the MATLAB itself. Okay, and here's I can also give a function. Function. This is a lecture 14W. I don't want the output, just the input KK. What is KK? I'll put KK here. KK should be an integer. Alright, KK should be an integer. Okay. Let's run it again. I give a 64. What will happen? Now I have three ways to calculate. The difference is quite small. Okay, that's fine. And the time codes, the first way I use like 20. After point I have 0, 2, 3, and the second fast one is 0, 0, 4. Right, it's fast, and T is even faster. It's a computer. The FFT in the MATLAB, it works more faster. They consider more considerable consideration. They consider more factors, make it even faster. Right? Now it's a 64. We can try. Can we find 64? Then 1 to 8. Double. The FFT is still 0. If I use 1, 2, 2, 4. What will happen? Last. Oh, it's slow. Yeah, it's okay. You see, the first one, original algorithm, it spent like a 7 second and half, like right, 7.5 seconds. And the second algorithm will make it faster. It's a 0.15 second. Or FFT still to be 0. Very fast. Try again. Yeah, the most time spent on the first one. Yes. Oh, can we check it? Just check the last two to see how faster they. Yeah, we do not do the first one. Do not do the first one. I just cancel it. Okay. Do not do the first one. I try the second and the third. Third one is FFT, and the second one is my FT2. Now is 1024. This one I times 32. What will happen? Oh, still too large. Sorry, I choose. Oh, it's not. Okay. The second method we use 11 second, and the FFT in the computer it is used .11 second. It's very faster than mine. Yeah, but you know what? I calculate. I write in this way. I use a function, right? So when I run this function, I need to go into another level of the function. So when I run it, I run several functions. Like if this is a xn size is 10,024, then totally I have 10 functions. I use 10 functions, right? When I run it, totally I have 10 functions are running in the system. And in the FFT, in the MATLAB FFT, it is just one function. The idea is the same with this, but it combines everything in just one program, one function. You do not need several functions to use another function. They combine everything together, so it run faster. Yeah. Okay. All right. That will be all for today. I just introduced you how to do these kind of things. Later, if you after you work, if you have a chance, you need FFT. Basically, if you work in the signal processing field, the use FFT is a kind of necessary work. You have to use FFT. But if you do not have MATLAB, what can you do? Okay, you can have things looks like similar like this. I think this one you transfer to be any kind of program like C or Java or any other kind of language programming. Similar thing, right? Similar thing. You can write the program similar like this. Alright, okay, that's all for today. Then Friday we will have a review of the whole semester. Alright, see you next time. Bye bye.